All right, good morning, everyone. I hope everyone's doing well. We've got our second day of our final exam review here, and I'm coming to you live, virtually from YouTube. Um, so today we're going to tackle our logarithms unit as well as our first trig unit, and we'll just dive right in. So this box here in the top left-hand corner, these are things that hopefully come back to you very quickly, but they're things that you should know for the final exam. These are our log laws. So the first one here, that's our definition of a logarithm. This is our multiplication law, our division law, our power law, and then this is our change of base rule. And one of the things we're concerned about when we're working with logarithms is our solutions and whether or not they fit into the domain of the particular logarithm. So if we remember some of our restrictions on logarithms, our argument has to be greater than 0. Okay, it would be impossible to create an argument that was 0 or a negative argument. And the other one is that our base cannot be 1. So if we keep those things in mind, we can go through and just identify what the domain is of each of these logarithms. Okay, so the first one, x here is our argument, and so we would just say that x has to be greater than 0. Our argument here is x plus 2, so we could create a little inequality. We would say x plus 2, which is the argument, has to be greater than 0. And so x has to be greater than negative 2. And the next one, our argument is 3 minus x. So we could do 3 minus x has to be greater than 0. Negative x has to be greater than negative 3. And now we need to flip the inequality. We would say that x has to be less than 3. These are our domains here. And the last one, so from the argument itself here, we would say that x has to be greater than 0. And restrictions on the base can't be 0, and nor can it be 1. So x has to be greater than 0, but not 1 is going to be all-encompassing there for that logarithm. Okay, next one. So we want to evaluate this logarithm to 4 decimal places. So we've got log base 3 of 45. We're going to use our change of base rule. I'm just going to write this out. We've got log base 3 of 45. And I can rewrite that using change of base as the log of 45 divided by the log of 3. And we can just punch that into our calculators, and we should get something like 3.465. I believe that's 0. Okay. The next one we want to write as a single logarithm, so we're going to combine these using our log laws, multiplication law, division law, power law. So the first thing I'll do is I'll use power law. So I'm going to rewrite 2 times the log of a as the log of a squared. And then minus 3 times the log of b, we'll write that as the log of b cubed. And then plus the log of c. Okay, so we want to pay attention to which of our logarithms are positive and which are negative, and we can combine to a single logarithm. The positive logarithms, the argument is going to comprise the numerator of our single logarithm. So we're going to have the log of, this is going to be a squared times c, all all over, and the argument of our negative logarithm becomes the denominator in the argument of our single log. There we go. Okay, next one. So we've got log base 4 of x squared plus log base 8 of x to the power of 6. So one of the things that I'm noticing here is that the two bases are different. So our log laws are out the window. What I'm going to use is change of base instead. So we'll use change of base. And see where we can go from there. So use change, use change, oh boy. Use change of base. Okay, so log base 4 of x squared, we're going to rewrite that as the log of x squared divided by the log of 4. And log base 8 of x to the power of 6, we will write that as the log of x to the power of 6 divided by the log of 8. Okay, so we're looking to add two fractions, and in order to do that, we need a common denominator. We don't have a common denominator, but what I do notice here is that both 4 and 8 could be rewritten as powers with a base of 2. So let's try that in our next step. So we've got the log of x squared, and I'm going to rewrite the log of 4 as the log of 2 squared. Okay. And then we've got the log of x to the power of 6. And we'll rewrite the log of 8. 8 we can rewrite as 2 cubed. Okay, so let's try using power law here, and we'll use that 4 times. So we're going to take the exponent from the argument, and we're going to move it out in front of the logarithms as a coefficient. So the log of x squared becomes 2 times the log of x. And this is over, and the log of 2 squared we can write as 2 times the log of 2. And then we've got 6 times the log of x. And 3 times the log of 2. And let's see if we can simplify those coefficients. Those cancel each other out, and we end up with 2 log x there. Okay, so our next step here is we've got the log of x over the log of 2 plus 2 log x over log 2. And sure enough, we've got a common denominator, so we can combine those numerators, which happen to be like terms. So we've got log x plus 2 log x is 3 log x. This is all over the log of 2. And so we could leave it like that, or we could use change of base in reverse, and we could rewrite this as 3 times log base 2 of x, or we could write it as log base 2 of x cubed. So all 3 of those expressions are equivalent to one another, and I would accept all of them for full marks. Okay, next one. So we've got 4 to the power of x plus 5 is equal to the square root of 2 to the power of 8x minus 6. And so what I want you to notice here is that both 4 and the square root of 2 could be rewritten as powers with the same base. Okay, so let's just leave a note for ourselves here. Let's convert to same base. Okay, so 4 I'm going to rewrite as 2 squared, and that's being raised to the power of x plus 5. Okay, the square root of 2, remember your fractional exponents. So the square root of 2 I can rewrite as 2 to the power of 1/2. And that's being raised to the power of 8x minus 6. Okay, power law of exponents. We've got to multiply those exponents. Make sure you're multiplying each term. So we've got 2 to the power of 2 times x is 2x. 2 times 5 is 10. And we've got 2 to the power of 1/2 times 8x is 4x. And minus 3. Okay, so now we've got a common base here. We can drop the base and we can evaluate the exponents. So I'm going to rewrite this just as 2x plus 10 is equal to 4x minus 3. And we should end up with 13 is equal to 2x. And so x is equal to 13 over 2. Okay, flip the page here. So next one, we've got log base 3 of x plus log base 3 of x plus 6 is equal to 3. One of the things that we could do right out of the gates is just look at the domain of each of these logarithms. So the domain of the first one, we would say that x has to be greater than 0. The second one, x has to be greater than -6. So the combined domain then, what values of x work for all of the logarithms? Values of x that are greater than 0. Okay, so that's what we're working with. Okay, so we've got log base 3 of x plus log base 3 of x plus 6 is equal to 3. So on the left-hand side, we've got the sum of two logarithms with the same base. So we could use multiplication law. And so what we're going to do is multiply the two arguments. So we've got log base 3 of, this is going to become, just open a set of square brackets there. This is x times x plus 6. And we'll make this equal to 3. And from here, we can use our definition of a logarithm, and we can convert this to an exponential. So we're going to go with the base, which is 3, raised to the power of the solution, which is 3, is equal to the argument, which is x times x plus 6. I will expand that out. We get x squared plus 6x. Okay, 3 cubed is 27. I'm going to move that to the other side. Leaves us with 0 on the left-hand side. 0 is equal to x squared plus 6x minus 27. Let's see if we can factor that. It should end up with 0 is equal to x plus 9 times x minus 3. And so our solutions for x are going to be -9 and +3. Now let's take those solutions and have a look at our domain. -9 doesn't fit into that domain, which is values of x that are greater than 0, so we're going to reject that solution. I'm just going to cross that out. rejecting negative 9 as a solution. Okay, next one. So we've got log base 2 of 3 minus 2x minus log base 2 of 2 minus x is equal to log base 2 of 3. So why don't we look at the domain of each logarithm before we dive into this. So log base 2 of 3 minus 2x. Log base 2 of 3 minus 2x. So the restriction is the argument must be greater than 0. So what values of x make this argument greater than 0? Any value that is less than 3 over 2. Okay, and the next one, log base 2 of 2 minus x. What values of x make this greater than 0? Values that are less than 2. Okay, so what values of x work for both of these? Anything that is less than 3 over 2. So we'll say combined values of x that are less than 3 over 2 or 1/2. Okay, so we've got log base 2 of 3 minus 2x minus log base 2 of 2 minus x is equal to log base 2 of 3. So we've got 3 logarithms with the same base. This is going to open us up to being able to use our log laws. On the left-hand side of the equation, we've got the difference of 2 logarithms, so we can use our division law. So I'm going to rewrite as a single logarithm here. We've got log base 2 of 3 minus 2x is our numerator. 2 minus x is our denominator. Okay, and on the right-hand side, we've got log base 2 of 3. Okay, now we've got single logarithms with the same base on both sides of the equation. Here we can drop the logs and just evaluate the arguments. Okay, so we're going to end up with 3 minus 2x over 2 minus x is equal to 3. And we'll solve from there. We get 3 minus 2x is equal to 6 minus 3x. And we're going to end up with x is equal to 3. Okay, now I'm going to look at our combined domain here. Is this a value of x that is less than 3 over 2? No, it is not. We're going to reject that. And so therefore, we have no solutions to this equation. All right. And the last one here is one of our word problems. First thing I'm going to do is just jot down our little party formula. And maybe we'll take the time here to just remind ourselves of what all these things represent. So P represents some final amount. And A represents an initial amount. R is our rate. It's a rate of growth. If it's positive, it's a rate of decay. If it's negative, when we're dealing with money, it's going to be a rate of growth. Okay, little t and big T. So little time is, little time. Little t is the passage of time. It's the amount of time that it has taken to get from the initial amount to the final amount, from A to P. Okay, and then big T is our time period of one rate of growth. Okay, so, well, we'll talk about these with reference to the question in just a second here, but I'll write this down. So big T is the time period for one rate of growth. Okay, now with respect to the question, so we invest $2,000 in an account that earns 6% interest that is compounded quarterly. How many years will it take for our investment to double? Okay, so we invest $2,000. This is an initial investment. It's our initial amount. It's our A value. Okay, the question's ultimately asking how long is it going to take for our investment to double? So that means our P value, or our final amount, is going to be 4,000. Okay, the time period for it to double, this is what we're trying to find out, and that's little t. So I'm just going to put a question mark there. That's our unknown value. Okay, so our rate of growth. So we've got 6% interest, and it's compounded quarterly. Okay, so interest rates are always annual interest rates. Now, the compound interest is when we are earning interest on top of interest. So every quarter of a year, every 3 months, we're going to get a quarter of that 6% annual interest rate paid out to us. And then the next quarter, we're earning interest on our initial amount, our principal investment, plus the interest that we have just earned. Okay, so our rate of growth here is we're going to take that 6%, and we'll convert it in just a second, and we're going to divide it by 4. Okay, we're going to divide it quarterly. Okay, so 6% as a decimal, 0.06. We're going to divide that by 4. It's 1.5%, which as a decimal is 0.015. Okay, and so our time period for one rate of growth, this is going to be 1 quarter. So this represents 1 quarter of a year. Okay, and our formula was this. So we've got P, some final amount, is equal to A, some initial amount, times 1 plus R to the power of little t over big T. Okay, so we'll plug those values in. So we're going to plug in 4,000 for P, 2,000 for A. We've got 1 plus R, which is 0.015, so we're going to get 1.015 inside the brackets. Little t is our unknown, and big T is 1 quarter. Okay, so we'll look to simplify this as much as we can. I'm going to start by dividing both sides by 2,000. So on the right-hand side, those 2,000s are eliminated. On the left, we're left with 2. So we get 2 is equal to 1.015 to the power of, now little t divided by 1 quarter is 4t. So we've got 2 is equal to 1.015 to the power of 4t. Okay, so Can we rewrite both sides of the equation as powers with the same base? I don't think so. So from here, we're going to need to log both sides. So I'm going to rewrite this as the log of 2 is equal to, and I'll use power law at the same time here. So I'm going to go 4 times t times the log of 1.015. Okay, and ultimately we're trying to isolate little t there. So we'll divide both sides by 4 times the log of 1.015. 4 times the log of 1.015. And so we should end up with something like 11.6. And so what that represents is the number of years that it's going to take for us to double our investment of $2,000 when invested at 6% annual interest compounded quarterly. And that's it.